Hello and welcome to this video for Chemistry 30, the equilibrium acid-base unit. Now, what I'm doing in this lesson is actually kind of just a quick review of pH and pOH calculations that you actually learned how to do in Chemistry 20. Now, there is one other concept that is kind of new and goes with what we've done so far in this unit, and that is the equilibrium constant of water. So water, to a very small extent, self-ionizes. And more accurately, what happens to a solution is that there is a transfer of hydrogen ions from something that has a donatable hydrogen, such as water, which can donate one of its hydrogens, to another water molecule, forming the hydronium ion, and when this loses its hydrogen, it's left as the hydroxide ion. Now, if I were to write the equilibrium expression of this, which we actually call Kw, because we don't include liquids, it would be the concentration of the hydronium ions times the concentration, well, let me close that bracket, times the concentration of the hydroxide ions. Now, I know that in neutral water, the concentration of the two ions are the same. They're both 1.0 times 10 to the negative 7. So if I put that value in for both of these, I get a value of 1.0 times 10 to the negative 14. This is known as the ionization constant of water. And why this is helpful is because it can help us find one of the ions in the solution, because they both need to multiply to add up to 1.0 times 10 to the negative 14. So that means, again, if we're trying to find one of the ions from the other, I just divide by Kw. So for example, if I'm trying to find hydroxide and I know hydronium, I take my Kw, 1.0 times 10 to the negative 14, divide by that hydronium ion concentration, which was 1.0 times 10 to the negative 4, and we will get an answer. Make sure you're using brackets around these. You should get an answer of 1.0 times 10 to the negative 10 moles per liter. Now, this is a quicker way of finding the ion concentrations, rather than finding pH first, subtracting from 14 to find pOH, and then so on. So this is a quick way to switch between the two ions, and comparing them lets you know what type of solution you have. If they're equal, your solution is neutral. If there's more hydronium ions, the hydronium ions are the acidic ions in the environment, then it's going to be acidic. And if there's more hydroxide ions, those are the basic ions in the solution, then the solution is going to be basic. So if we do some examples of this, if you have 1.0 times 10 to the negative 9 for hydronium and you take Kw, 1.0 times 10 to the negative 14, and divide by that, you get 1.0 times 10 to the negative 5. Comparing the two ions, these are negative exponents. So this is 0.000, there should be 1, 2, 3, 4, 5. This is 0.1, 2, 3, 4, 5, 6, 7, 8. Okay, so those negative exponents are how many, if I move the decimal place over. So the lower the negative exponents, actually, the greater the concentration it is. So the concentration of the hydroxide ions is greater. And so therefore, this is a basic solution. This is why we deal with the pH and the pOH scales, because the concentrations are usually very small. So this gives us the ability to use larger whole number or not such tiny numbers. Next, we would get 1.0 times 10 to the negative 13. That would be acidic. And the last one we would have, the last one on the slide anyway, would be 1.0 times 10 to the negative 12. That one, the greater concentration of hydroxide ions, so it's basic. And then a couple other examples. Hydroxide here would be 1.6 times 10 to the negative 6. That's greater than hydronium, so it's basic. The next one, the hydroxide ions, would be 1.2 times 10 to the negative 12 moles per liter. The hydronium is greater, so it's acidic. And the last example here would be 3.6 times 10 to the negative 8, which would give us a slightly basic solution. They're pretty similar, but in order to be neutral, they have to be exactly the same. Okay, so again, if you are trying to find hydronium, you take Kw and divide by hydroxide. And if you are trying to find hydroxide, you take Kw and divide by hydronium. Kw, again, being 1.0 times 10 to the negative 14. That is in your data booklet on page 3 where your constants are. Now, what are the other formulas we learned in Chem 20? So remember, when you have a hydrogen-containing compound, usually starts with hydrogen, and I put that compound in water because remember, these are all solutions being placed in water. My hydrogen is actually leaving the acid,
Chris Nimboli to the main office,
transferring to the water to make the hydronium ion, and then the anion is left on its own. So whenever you have a compound, again, that starts with hydrogen, with some exceptions where the hydrogen is bonded to the end of those organic acids, you have an acid. You therefore have hydronium ions. If you take the negative log of those ions, that will give you a number on the pH scale. Think of H for the hydrogen from the acid. Okay, but the hydrogen doesn't just exist by itself, it bonds to water to make hydronium. Bases, if they're a strong base anyway, they are an ionic hydroxide. So they are a cation bonded to hydroxide, and they do not react with water. They just simply dissociate into the number of hydroxide ions that are based on the compound. Okay, so if this was magnesium hydroxide, I would have 2 hydroxide ions. When you have an ionic compound with hydroxide, again, that's a base, and therefore you have hydroxide ions. When you take the negative log of those, you're getting a number on the pOH scale rather than the pH scale. Okay, but the two are related to each other where you can find one from the other by subtracting from 14. So pH can be found with 14 minus pOH, and pOH can be found with 14 minus pH. Okay, I can also find the concentration of my 2 ions. Hydronium can be found with 10 to the exponent negative pH, and hydroxide concentration can be found with 10 to the exponent negative pOH. Now, there's also a special significant digit rule for pH and pOH. Okay? Whenever we're dealing with everything we've measured in Chem 30, mass, moles, concentration, volume, all of those values, our sig digs are always the total digits, excluding any leading zeros. If it's in decimal form and it's 0.0 something, those leading zeros are excluded. So we are looking at total digits as being significant in most of our calculations. But when I have a number on the pH or pOH scale, the only thing significant in those values are their decimal places. So the number of decimal places or digits after the decimal place. So if I am given concentration, I look at the total digits in the concentration to tell me how many decimal places I should have in my pH. And then if I have pH or pOH, I look at its decimal places to tell me how many total digits I need in my mass if I'm solving for mass, for example. Okay, so let's look at a few examples. I have hydronium ions, and I'm asked to find the pH, so I just have to take the negative log. Those are the ions I need to find pH, so I just take the negative log of them. And then again, when I'm looking for my sig digs, I have 2 total digits in my concentration, which means I need 2 decimal places or 2 digits after the decimal place in my pH. Okay? Total digits in concentration, mass, volume, moles, all of those are total digits. That needs to match the decimal places in the pH. Okay, another example, find the pH. Well, we have hydroxide ions, so we're not going to be finding the pH. We're actually going to be finding the pOH first when you have hydroxide ions. So when we take the negative log of those, we get the pOH, and then I subtract it from 14 to get the pH. Again, I have 2 total digits in my concentration, so I need 2 decimal places in my answer, 11.38. Okay? Next example, calculate the hydronium ion concentration if the pH is 5.25. So now I'm going to go 10 to the exponent negative pH. Now I was given the pH. What's significant in it are its decimal places. There are 2 decimal places, so that has to equal my total digits in concentration. Again, pH and pOH sig digs are its decimal places only, the number of digits after the decimal place. Concentration, mass, volume, those are all total digits. Okay, so decimal places equal total digits here. 5.6 times 10 to the negative 6. Now let's say we're given a question where we have a compound. Okay, and I should have a dissociation equation. I guess it's just skipping that. Let's write this out. I have a compound and I am asked to find pH. Now, first thing I need to do is figure out what type of compound do I have. Do I have an acid or a base? This is an ionic hydroxide, so it is a base. When you have a base, you do not react it with water. Only acids react with water. Weak bases will react with water, but for Chem 20 review, we focused only on strong bases. Strong bases are all ionic hydroxides, so they will always just dissociate. Okay, now I have the mass of the calcium hydroxide, 10.3 grams. Molar mass is obviously something I can always find. I think it was 74.10 from the periodic table. And so I can find the moles with mass over molar mass. 10.3 divided by 74.10 gives me 0.139 so on moles. Now I can take those moles and divide by my volume in liters. So I have to divide that by 1,000. That's 0.500 liters. So when I do that, this gives me the concentration of my given. I am given the information to find the concentration of the solute, the compound, the base, whatever you want to call it. And in order to find pH, or actually in this case we'll be finding pOH, because I have hydroxide ions, I need to take the concentration given and multiply by wanted over given, which is 2 over 1. So this again is going to give me the concentration of my ions. Whenever you're doing pH and pOH calculation, you need to find the ions, either the hydronium or hydroxide. The type of ions you have depends again on the compounds that you have. If you have an acid, it will react with water to make hydronium. If you have a base, it'll just dissociate to make hydroxide. So now that I have my hydroxide ions, I can take the negative log of those, again remembering that this is going to give me a number on the pOH scale. Do not round early, especially when you're taking negative logs. It'll give you a really wrong answer. So my pOH is 0.254 so on, and I am looking for pH. So it'll be 14 minus that value, unrounded again. And I get an answer. Now I'm looking at total digits in the question. Those are masses and volumes. And that has to equal my decimal places because this is a pH value. So 13.745, 3 decimal places to match my total digits in mass and volume. Okay? I have a couple of sample diploma questions, and then that's it for this review. So let's say you're asked to find the hydroxide ion concentration. I know in order to do that, I can go 10 to the negative pOH. Except I don't have pOH, I have pH, but very easily I can get pOH, by subtracting it from 14. pOH equals 14 minus 3.38. 14 minus 3.38 gives us a value of 10.62 for our pOH. That's an equal sign there. So in my calculator, I hit 10 exponent negative 10.62. 10 to the exponent negative 10.62. Hit enter, and you get 2.4. Again, I have 2 decimal places, so that has to equal my total digits times 10 to the negative 11 moles per liter. The question asks you to leave it in scientific notation and record the values of A, B, C, and D. So it'd be 2, 4, 1, 1. Okay? And then the second sample diploma question, you have a solution with a pH of 3 compared to a solution with a pH of 5. The solution with a pH of 3, so the lower the pH, the more acidic it is. When it's more acidic, it has more hydronium ions. So the answer would be B. Now, it could also ask you how many times the concentration is changing. Remember, for each level you change on the pH scale, the concentration changes by 10 times. So it's 10 to the power of 2, or 10 times 10, which is 100 times that the concentration is changing during this, I guess if you're diluting it or whatever the case is, to make it go from a pH of 3 to 5. Okay? The next lesson is going to look at pH calculations when we have weak acids and bases as well as the strong ones, just kind of reviewing that again, and then you'll learn how to do that in those lessons. Thank you for watching.